So I will be presenting on behalf of my teammates Irene Foster, Sunshine Schneider, and Caitlin Timmons on our project Storm Chasers, synthesizing New England weather data on a dashboard for emergency response workers. So the motivation behind our project was to create an interactive dashboard to help first responders in New England make data-driven decisions on where to direct their efforts during natural disasters. And just as a reminder, New England consists of Massachusetts, Connecticut, Rhode Island, Maine, Vermont, and New Hampshire. So why New England? Well, first, Smith College is located there, so might as well choose a place close to home. But it has a history of extreme winter weather, such as hurricanes, freezing, winter storms, and droughts. There's also an increased risk of flooding from climate change. The Northeast actually saw a 70% increase in the amount of rainfall between 1958 and 2012, which is more than anywhere else in the US. Additionally, the Northeast has many contaminated industrial sites. It's home to some of the oldest buildings and infrastructure in the US. Also, there's already an existing network of disaster relief organizations, but there's no existing open access tool that consolidates relevant geospatial and weather data for first responders. So our methods. Well, we consolidated relevant landmarks, demographic information, and weather conditions into a single dashboard, and we did this using 8 entirely open source data sets. So I'm going to quickly run through those. The New England Dams database has 7,437 observations and is the location of active and inactive dams in New England, and the dams are classified by their hazard level, so how much damage it would cause during a collapse. The New England Landfills database is the locations of active and inactive landfills in New England, and it was compiled by the EPA. It also includes the amount of waste in each landfill, which is essential. The EPA Superfund sites are point locations of hazardous and toxic sites in New England, and these are the most dangerous sites to the environment and human health. The NOAA Historic Storms and Climate Data online databases, they record occurrences of storms and other significant or rare weather events with the potential to cause economic damage or loss of life. The National Weather Service forecasts are weather observations from weather stations in a given zone, and there are variables such as temperature and precipitation. And the CDC Social Vulnerability Index, or SVI, which is assigned to each county in the US, and it measures the resilience of communities, meaning the ability to survive and thrive when confronted by external stresses on human health, such as natural or human-caused disasters, disease outbreaks, and more. Finally, the 2019 American Community Survey. This is an annual nationwide survey that collects information on age, disability, educational attainment, health insurance coverage, median household income, and more. So here's all of our data in one page, and I will tell you how we were able to get through all of these variables in a second. So it's also important to note why we specifically chose some of these variables. If we're measuring data about weather, why do we care about social vulnerability? Well, natural disasters tend to impact low-income communities of color the worst. They're often not able to evacuate, and they're more vulnerable to flooding due to worse infrastructure. Additionally, FEMA, after disaster occurs, tends to give more aid to white victims rather than victims of color, despite the damage being the same. So we felt it was essential to include information about this as well. So our methods, well, first we had to build the dashboard, which we created using R, Shiny, and Leaflet. All of these data sources were synthesized, so each one's a layer on a map. Some were point data, some were shape data, and multiple data sources can be viewed at the same time. You can toggle things on and off. Additionally, we created a predictive modeling for flash flood risks. We did this training a random forest model to predict whether or not a flash flood will occur with 93% accuracy given weather conditions and date time information. We implement this model onto our dashboard to provide real-time flash flood risks at a county level in Massachusetts. So a little bit more about the predictive modeling for flash flood risk. We did this by training and optimizing the model using historical weather and climate data from NOAA and land usage data from MRLC. So first we did correlation analysis, which helps us identify the highly correlated features, which we then remove from the historical weather data set. Then we did recursive feature elimination, which is an algorithm to help us identify features with the highest predictive power. So from that information, we were then able to determine that we will be using 5 features: daily precipitation, daily maximum temperature, month, day of month, and time of day. We then tested and tuned SVM and random forest classifiers with and without resampling. You can see in our table that random forest without resampling produces the best results. Finally, we wanted to integrate current weather conditions so that way we'd be able to predict flash flood in real time. So we did this by accessing current weather conditions through the National Weather Service API and average temperature and precipitation measurements at a county level in Massachusetts. We then use our tuned random forest model to predict the current flash flood risk for each Massachusetts county. And you can see what the data looks like at the time of the screenshot. There were no flood predictions occurring, but that is what it looks like. And all of that, it was a lot. So here's just one machine learning workflow to kind of consolidate it together. If you want to look at it a little bit more in depth, it is on our paper. So our insights, this is what the dashboard would look like if the social vulnerability index was toggled on. We also had a data tab, so that way first responders would be able to quickly look at what data they needed for whatever specific event was occurring, and then decide what they wanted to toggle on and off. So using Worcester, Massachusetts as an example, we see that it has an SVI of 0.6923, a number of floods since 2018 of 27, a population density of 570.68, and a median household income of $79,142. We see a high concentration of dams, both active and inactive. Additionally, a high concentration of EPA Superfund sites and 2 landfills, which not a lot, but still significant. The reason why we use Worcester, Mass as an example was in July 17, 2018, there was a massive flash flood that was devastating and no one expected it. Had our dashboard been active at that time, given the data from that day, we see that we would have been able to predict that flash flood and we could have helped resources go that way. So our conclusion, we just hope that our work helps to inform disaster relief workers to predict flooding events and decide where resources should be allocated. Our in-depth paper can be found on the eUSR ESP Fall 2022 page, and our dashboard's been published as a Shiny app. So thank you so much from Team Storm Chasers.